Welcome to today's webinar, DOCSIS 3.1, Plans and Strategies. I'm Mike Roebuck, Senior Editor with CED. Today's webinar is sponsored by Cisco and ARRIS and hosted by CED. Just a couple of quick programming notes before we get underway. There's a button to make the presentation screen larger. Also, you can download a PDF version of the webcast slides. Make sure you ask questions throughout. We'll get to those near the end of the hour. We anticipate having a lot of questions. There's a lot of people signed up for this webcast. And then lastly, the webcast will be archived on CED's website probably sometime tomorrow. So obviously 3.1 is a timely topic for the industry. We had the symposium at Expo last month. The CableLabs product specs came out last week. So we're hitting this right at a good time. We're going to start off with Jeff, and he's going to provide an overview of 3.1 and why it's needed. And then IAM is going to take over, and he's going to talk about the PHY layer, followed by John Chapman, who will give us an overview of MAC. Then we're going to close out this webinar with George Salinger from Comcast. He's going to talk about DOCSIS 3.1 migration and use cases. So with that, I'm just going to go ahead and hand it over to Jeff and let him get started.
Thanks a lot, Mike. Good day, everybody. What I'm going to do is I'm going to talk a little bit about what got us to the point that we realized we needed to go forward with DOCSIS 3.1, give you a little bit of overview into the different changes going on in the industry, some concepts about speeds and what's really driving that, and then talk a little bit about what we as an industry believe we're really going to get out of DOCSIS 3.1. So when I think about it, I think about this concept of how we have been dealing with media over the history of the cable industry. And there's this classic view where when you wanted to consume media, that you would be in front of a TV in your living room or dining room or wherever it happened to be, and that's just where you had to sit. When it came to the time when you could watch it, that it was always at a predetermined time. There was one device that you consumed it on. It was a very passive experience. And you really couldn't just move this around with you into different places in the house. There's a much more modern view where there's no absolute space, so that your media is always with you. You have your between smartphones and tablets, laptop computers, devices in cars. There's all sorts of gadgets that are out there that allow us to take our content with us, whether it's video, whether it's books, internet access. You're never able to really disconnect, which is both a blessing and a curse. So this entire concept of where you consume has changed dramatically. Now, there's also no absolute time. Everything gets time shifted. You have the ability to store it either in the cloud or on the device. We have DVRs at home. There are all sorts of ways in which we can actually look at this content and turn it into a very individual consuming of that information. It's across multiple platforms. It's no longer just the TV. It's no longer just standard def. There's 720, 1080i, 1080p, 4K now. There's the screens on the tablets, on smartphones. Even now, people are starting to work on watches that actually interface into the internet and into various devices. So there's a very large convergence of these devices where you have to deal with multiple formats of this media. It's a very interactive experience. You're no longer just sitting there and having it fed to you, that you're able to define what I like to call a me-cast, because what I consume is built for me, and I've built it for myself so that I get that content in the format in which I want to see it at the times I want to see it. Somebody has described this as we, what I want, where I want it, when I want it. And basically, the consumer, you become the producer. You're the one who programs your own content so that that content is accessible to you on demand at the time in which you want to see it. Now, there's behavioral changes that change around this. So from a provider perspective, we have to deal with this with many different kinds of delivery vehicles. It's no longer just MPEG transport over a coaxial medium. We now have to deal with not just MPEG-2, MPEG-4, soon H.265. We have to send it across coax, fiber, wirelessly. When it comes to the content and social media side, people get this, get devices not to keep it in the home, but they're putting their lives online. That the number of pictures you see of somebody's meal on Facebook, it constantly amazes folks. And that just comes down to that whole social media, where at the same time it's fascinating, it also in some ways is impacting how people use this media. So when you look at the consumer's perspective, people are changing from consumers to producers. So you don't buy digital cameras just to take the picture and keep it on a device at home. You take it and you upload it to Facebook, to Picasa, to various sites out there on the internet, which make it possible for others to have this sort of experience in what's going on in your life. There's the OEM devices that, if you look at what devices have become today, and if you look at your smartphone, and if you look at your TVs, these are really graphical user interface devices, that the cloud is now the storage, that it almost harkens back to the days of X Windows, where this client-server paradigm for displaying content with all of the intelligence actually being in the precursor to the cloud really took place. So what does this drive us to? So one of the things that we always talk about is, what are these speeds that we offer? So we draw this curve, and it's been called the Nielsen curve, where you take these speeds and they keep increasing linearly on a logarithmic scale over time. And if you go back to the early days with 300 baud dial-up modems, and you just plot that line forward, you can find all these different points on the line, and you can see that this is eerily accurate. And we layer on top of this these different eras of technology. So let me point out that these are the top Billboard speeds offered. These are not what everybody gets. So if you look at what these times were during the dial-up era, it pretty much got us through to bonding 56K channels and even to 64K. And technology came about, which eventually became known as DOCSIS. And this is where the DOCSIS 1.0 and the 2.0 eras came out, where you had a single downstream that a modem could tune to. And that got us up to somewhere around the 30 or so megabit per second mark. And at this time, people came in through CableLabs writing the next generations of specs, which became DOCSIS 3.0, where now you are able to bond channels. And you can bond 24 channels, 32 channels. You could even bond many more channels if you so chose. But there's got to be something that comes beyond this. And what we see is, if we look at where we are today, what we see in here is that there is capabilities in 32 by 8 modems, 32 downstreams, 8 upstreams. You look at how much you can do in a 1 gigahertz plant at 256 QAM. And then we draw this line and shows this is where we are today. And amazingly, this is pretty much where we are today, that we're at about as high as 150 megabits per second if you're bonding 8 channels. And we did this analysis and said, well, there's this other line that follows it. And this line is the weighted average line, and this drives the total bandwidth needed and how many complete bonding groups. So you can see that there's something that occurs after this, and this is where DOCSIS 3.1 comes in. And DOCSIS 3.1 adds a lot of capabilities, and it gives us the ability to do as much as if we would have the spectrum available and the plant was conditioned as such, to get up to 10 gigabits per second downstream. So you can see that this extends the life. Now, we can argue about whether these lines will continue at the same rate. Maybe that bottom line flattens out a little bit. But it's easy to see that there's a finite point where DOCSIS 3.0 can get us for the entire market, and it will go much longer in certain segments of the market. But even beyond here, there's got to be something next, which I sort of tongue-in-cheek call the next generation access network. And then you can see where this line comes in at 4096 QAM with DOCSIS 3.1 and how far that can really get us. So what is this really doing is what DOCSIS 3.1 gives us is it improves the availability and reliability, because now we're dealing with OFDM, and others will get into much greater detail on this. It powers new business opportunities. It gives us much more bandwidth, much more stability with its capability of dealing with impairments on the plant. We're changing the way we provide this content. We're making it personal and portable. With this increased capacity and speed in spectrum management, we're enabling new services which before were never really possible over the cable network. So this really evolves our capabilities, and what it really will get us is it gives us more speed, higher order modulations, wider channels, more efficient use of the upstream, whether we are at 42, 65, 85, or even possibly 200 with higher order modulations. It gives us that ability to grow the upstream and add more capacity. It gives us the ability to have better scale, more density, consume lower power, and also get more bang for the buck out of the footprint that we have. We get this convergence of all of the different platforms over our different delivery mediums. And equally, what we get out of this are better economics, as we can get more out of the plant, doing less and less with continuing node splits, which are inevitable. But it gives us the opportunity to do that at our time, not at the time dictated to us by needing more and more capacity, which we normally get through node splits. So with that, let me turn it over to Ayam Albana, who is the Staff Systems Architect in the CTO office at ARRIS, and he'll get into some of the more details of the physical layer of DOCSIS 3.1. Ayam?
Thank you, Jeff. Good morning, everyone. This slide talks about the main technical features of the DOCSIS 3.1.5. The very first technical feature is the expansion of the upstream and downstream bandwidths. The second feature that DOCSIS 3.1.5 introduces is the use of OFDM as a new transmission technology. OFDM is a multi-carrier technology that stands for orthogonal frequency division multiplexing. And I'm going to explain it a little more in the next few slides. The third main feature that is introduced by DOCSIS 3.1.5 is the introduction of low density parity check forward error correction technology. And the last but not least feature is the increase in modulation orders up to 16K QAM in the downstream and up to 4K QAM in the upstream. So to go in a little more details about these features, we start with the first feature, which is the expansion of the upstream and downstream bandwidth. So this is still based on the high split architecture, where the upstream bandwidth is located below the downstream bandwidth. This is similar to today's networks. The upstream bandwidth that is supported by DOCSIS 3.1 is going to be 5 to 204, although wider is permitted but not specified by the spec. Other permitted upstream bands are 5 to 42, 5 to 65, 5 to 85, and 5 to 117 megahertz. The downstream spectrum is also expanded. It starts from 258 megahertz, although the spec recommends a lower start at 108 megahertz, and it ends well above the 1 gigahertz limit that is specified by DOCSIS 3.0. In particular, DOCSIS 3.1 downstream spectrum ends at 1.218 gigahertz with an optional support for 1.7 gigahertz. The next slide talks about the OFDM. OFDM, like I said, stands for orthogonal frequency division multiplexing, and it is a multi-carrier technology that is different than the single carrier technology that is currently used in DOCSIS 3.0. The main difference between OFDM, or the multi-carrier system, and the single carrier system can be explained at very high level as the difference between the shower head and the faucet. So if we assume that both systems, the shower head and the faucet, have the same capacity because both have the same size water pipe feeding them, then the only difference between these two systems is the way we stream the water. In the OFDM, or the multi-carrier, or the shower head example, the water stream is divided into multiple smaller streams. However, in the faucet, it is still one fat stream of water. Somebody might wonder and say, why bother about the complexity or the perceived complexity if I have the same capacity? Well, ideally, they have the same capacity, but real world is never ideal. For example, if you try to block one of the shower head nozzles with your finger, nothing much is going to happen. Most of the streams will keep going. However, if you try to do the same thing with the faucet, the water will go all over the place. This is basically the main benefit of using multi-carrier over single carrier, which is noise and interference robustness. Your finger here represents a narrowband interference. To go one level deeper about the difference between multi-carrier and single carrier systems, I show this graph where single carrier system is shown on the left side and multi-carrier system is shown on the right side. You can see that symbols are sent sequentially in the single carrier system, and since each symbol modulates the whole channel bandwidth, the wide spectrum, the duration of each symbol is small. On the other hand, in multi-carrier systems, the signal is divided into smaller signals, like the smaller streams in the shower head example, and each of these streams carry a symbol. So you can see that the width of each symbol is small, so that the duration is very long. And this has good benefits, as I'm going to show next. Note that the trapezoidal shapes on the top of the multi-carrier systems are actually subcarriers of sync waveforms that are overlapping but also orthogonal. So I would like to show the benefits of this single carrier versus multi-carrier systems in the presence of different kinds of noise. This is at high level. If we show an ingress noise, which is a narrowband interference hitting both systems, you can see that it affects all symbols in the single carrier case, and it affects a small number of symbols in the multi-carrier case. So all of them is much better in terms of noise robustness when it relates to ingress noise. When it happens that wideband impulse noise is hitting the system, you can see that symbol S2 got hit in the single carrier case and it was lost. Although on the multi-carrier case, it appears that all symbols are being hit, the long symbol duration and the FFT transform operation helps dilute the energy of the impulse noise to make it look like additive wide-Gaussian noise and offers more robustness to the OFDM case. So the OFDM gives better performance in the presence of ingress noise and additive wide-Gaussian noise. To give you a feel of DOCSIS 3.1 parameters supported and related to the subcarrier spacing, 25 kilohertz and 50 kilohertz subcarrier spacing are supported, and the channel bandwidth is up to 192 megahertz in the downstream and up to 96 megahertz in the upstream. Now, the multi-carrier signal is composed of these individual subcarriers. Not only that's important for ingress noise mitigation, but also we can turn on and off these subcarriers to accommodate legacy channels. So spectral holes can be made in the OFDM signal to make it live side by side with existing legacy channels. Now, the control of each of these subcarriers is also helpful because I can assign a different modulation order for each subcarrier based on the SNR value. This figure shows the SNR variations at high level. You can see that subcarriers that lie with high signal-to-noise ratio can be assigned high-order modulations, while subcarriers that lie in the low signal-to-noise ratio regions can be assigned lower-order modulations. And subcarriers that lie on the top of very strong narrowband interference can be muted. So this flexibility of assigning different modulation orders to different subcarriers based on their SNR performance provides the most optimum performance and most optimum throughput that can be offered by this technology. Mike, can you please advance the slide for me?
Is it the summary slide, IHAM?
No, this is good. The second slide is good. So this slide that's shown is another set of tools that are provided by OFDM is the presence of frequency interleaving and time interleaving. And frequency interleaving is helpful in mitigating the effect of narrowband interference, and the time interleaving is helpful in to mitigate the effect of impulse noise. There are other mitigation tools that are like the cyclic prefix and also the windowing. Low density parity check codes are the new forward error correction technology. They have been invented many years ago, but couldn't be used until recently. And this is because they require a lot of processing complexity. But recently, the evolution in processing speed allowed them to be used in many standards. These codes are much more efficient than the Reed-Solomon codes that are used in DOCSIS 3.0. They offer anywhere between 3 to 6 dB of gain. The downstream system in DOCSIS 3.1 offer long code words for better efficiency, and the upstream offers variable code word length to accommodate the user traffic. So the next slide, we apologize for the missynchronization between the slides shown and what I'm talking about. Looks like the tool is stuck.
What slide do you want up, IHAM? Do you want it near the end?
Would like the capacity slide, the table of the downstream capacity slide, please.
Okay, see, that is...
If you keep going, please.
This one? Well, the summary came up. You want capacity, right? You said?
Yeah, 2 slides before the summary.
Okay.
I'm showing here the first slide.
I don't know if we have more than one person pressing. Let me try it one more time here. Let me just hit next. I think we're in John's slides now, aren't we? So you want slide 18 up, is that correct?
Okay. If you keep going, yes, it should be around slide 19.
DOCSIS 3.1 U.S. capacity potential?
The previous one, the downstream. Although I don't view it on my slide, I can talk to it. Basically, I'm showing a table to show the downstream capacity potential. This table contains analysis for the downstream spectrum that's supported by DOCSIS 3.0 and the downstream spectrum supported by DOCSIS 3.1. The table shows many numbers, but the key number that we need to look at in this table is that DOCSIS 3.1 downstream throughput can be well above 17 gigabit per second, which is 184% improvement over what DOCSIS 3.0 can offer. The next slide, which contains the upstream capacity potential, contains similar analysis for the upstream spectrum shown by supported by DOCSIS 3.0, which is 5 to 85, and also the same analysis is done for upstream spectrum supported by DOCSIS 3.1. Examples are 5 to 200 megahertz and 5 to 300 megahertz. And again, there are many numbers shown on this table, but one of the key numbers here to notice that the upstream throughput can be well above 2.7 gigabit per second, which is more than 613% compared to DOCSIS 3.0. The last slide that I have in my section is the summary of DOCSIS 3.1 features, which are the expanded upstream and downstream bandwidth, the use of OFDM as a transmission technology, the use of LTPC forward error correction to provide significant improvement over the current Reed-Solomon FEC, and the use of higher order modulations to offer more bits per symbol. Note that enabling DOCSIS 3.1 requires little to no plan changes, and DOCSIS 3.1 enables more than 17 gigabit per second downstream throughput and more than 2 gigabit per second upstream throughput. Now I would like to carry the slides to John Chapman, who is a Cisco Fellow and CTO of the Cable Access Business Unit in Cisco, and he will talk about the MAC of DOCSIS 3.1. John.
Thank you, Ayam. So what Ayam really told you was that we've got a new PHY layer in DOCSIS 3.0 and 3.1. And I think that there's two fundamental things to take away from Ayam's presentation. One is that the new PHY layer uses OFDM, which is a slight change in the way modulation is done, and it makes it more robust in the presence of noise. But the real killer thing about this new PHY is that it has a new forward error correction called LTPC, which gives you the equivalent of 5 to 6 dBs extra resiliency to noise. Now, what does that really mean to you? What it means is that anywhere in the plant where you could run 256 QAM today, which is what everybody does, you're going to be able to run 1024 QAM with DOCSIS 3.1. You're going to go from 26 QAM, which is 8 bits, to 1024 QAM, which is 10 bits. That's a nice 25% bonus. But the bonus plan doesn't stop there. It turns out there's another 6 or 8 dB of variation on the plant. If you actually take a look at a well-engineered plant, there's just different noise levels around that plant. We have something in DOCSIS 3.1 called profiles, which allow us to take advantage of that next 6 dBs so that you could actually have some of the plant running at 1024 QAM, other parts of the plant running at, let's say, 2K QAM, and some plants actually running at 4K QAM. And if you compare 256 QAM to 4K QAM, which most of us thought was impossible just a few years ago, that's a 50% throughput that you can get with DOCSIS 3.1 on parts of your plant. So how do we manage that? Well, it turns out we can talk to these cable modems. We can actually go to the cable modems and we can measure the signal-to-noise ratio at each cable modem. And not only at each cable modem, but at each frequency within that OFDM spectrum, we can measure the signal-to-noise ratio. We can take that back and we can make a determination of exactly what modulation to give that cable modem. Now, it turns out it's a well-engineered plant, so we don't have to have a profile per cable modem. We can make things a lot simpler. We can maybe have 4 profiles, and this example I have on this slide demonstrates this. Now, the specification allows you to arrange profiles anywhere you want, but it's nice to have an illustrative example of how things work. We have a study on here of 20 million cable modems on a plant and the signal-to-noise ratio that was measured with a single carrier QAM across those modems. And it shows a nice distribution from around 33 to 41 dB signal-to-noise ratio. The higher the signal-to-noise ratio, the higher the modulation you can put in the plant. So really, if we could measure the SNR at a particular modem, we could bin them into different use cases. We could have a worst case, an average, a better case, and then a really, really good case. And we could assign each of those different modulations. And that's exactly what we were planning on doing with DOCSIS 3.1. So, maybe your average case is 1K QAM, and your better case is 2K, and your really good case is 4K. That's a very powerful feature. Now, on our next slide, let's take the concept of profiles and actually lay this down against a frequency plan. As you probably know by now, we're looking at a new frequency plan for DOCSIS 3.1. Now, this isn't a mandatory plan. You can fit DOCSIS 3.1 within your existing plant. So if you have a 42 or a 65 megahertz return path in the upstream and a 750 or 1 gig plant in the downstream, you can use DOCSIS 3.1. But where it gets really exciting is if you expand your upstream spectrum, and we put some new numbers into this spec. We recommend a 204 megahertz upstream spectrum. We're also recommending that you can take your downstream spectrum all the way to 1218 megahertz. So that's about 200 megahertz past where the current spectrum is for DOCSIS 3.0. If you do that, you're going to get more throughput. Not only do you have higher order modulations to work with, but you've actually got more spectrum to work with. Here we see an example of DOCSIS 3.1 applied to the spectrum. Because the 3.1 channels can be as large as 192 megahertz, you can fit the entire spectrum in 5 channels. And the upstream is going to be two 96 megahertz channels. Now, I haven't shown DOCSIS 3.0 in here, and I haven't shown video in here. The spectrum on the plant will actually have to share between 3.0, 3.1, and video. But it does show what we can do with the OFDM technology that is in DOCSIS 3.1. Now, how does a cable modem get onto a network? There is some of the things that we changed. Since we've gone to a new order of modulation, we've rearranged the data channel. If I take a look at the data channel, it looks something like this. There's one big channel. We recommend that it can be anywhere from 24 megahertz up to 192 megahertz. Now notice with 24 megahertz, we picked a number that both 6 megahertz and 8 megahertz divides into. So you no longer have different channel allocations for Europe and for the United States and for Asia. We all really have the same channel plan now, really big channels. There's a couple of things here. We have a data channel. We have something I'm going to talk about called an excoder pointer, which helps decode the data channel, and a filing channel, which helps organize things. The filing channel, or PLC, it's a 1 megabit per second channel. It provides basic needs such as timestamps, energy management. It also has a preamble in it that allows cable modems to lock on to the channel. So it's not necessary for the cable modems to go out and find the full OFDM channel and to figure out whether it's 24 or 192. It just has to find a preamble on the PLC channel, and once it finds that, we'll give it the configuration information for the larger data channel. We'll actually download a profile and a config file that tells it what to go and lock onto. So, what is the boot procedure for a cable modem? How do you wake up a cable modem? So to kind of reiterate, a cable modem will wake up, it'll go out and find the pilot, the PLC channel. It'll use the pilot pattern, which surrounds the PLC channel. We've got some dedicated carriers on either side that it can recognize, and of course the preamble. It comes up, it'll pull off the, we have a new timestamp. In DOCSIS 3.1, we have an 8-byte timestamp that provides not only backwards compatibility to 3.0, but it provides full time of day inside the timestamp, plus higher resolution down into the sub-microsecond. It's actually down into nanoseconds. It then goes into the message channel of the PLC, and it pulls out an OFDM channel descriptor. So it learns about the OFDM channel. It pulls out a profile descriptor for profile A. Profile A is kind of what we call our boot profile. So when a cable modem comes up, they all get assigned to profile A, which is, let's say, your 256 QAM, or maybe it's a 1K QAM. And from there, we start doing our test and measure of the cable modems. Either the CMTS can do test and measure or the cable modem can do it, and from there it can add in additional profiles. Now that's an interesting thing. A cable modem can actually be members of multiple profiles. It could receive its MAC management messages on profile A and its data on profile D, and we could be running a multicast on profile C. So we actually have multiple logical paths down to the cable modem that the CMTS manages. There's another interesting feature that we've added to 3.1, and that is a native energy management mode in 3.1. We have modified our protocol so that we can get the maximum energy efficiency out of a cable modem. And really the way to get the most energy, maximum energy efficiency out of a cable modem is to put it to sleep. By putting it to sleep, actually shutting down the PHY altogether. Now when you shut down the PHY, it introduces an interesting problem in that you can't talk to the cable modem anymore. For those of you familiar with 3.0, we have an energy management mode where we drop from 8x4 down to 8 channels down and 4 channels up, down to like 1 down, 1 up, but the PHY was still on. Here we allow the cable modem PHY to turn off, and we manage it with a sleep timer. We fundamentally tell the cable modem to go to sleep and to wake up at a specific value of timestamp. When it wakes up, we either tell it to go back to sleep or we tell it to wake up. Now, in order to make that work, we actually have to hold on to all the packets for the cable modem at the CMTS. And so you'll see on the slide here something called a DLS buffer that holds all the packets. When we wake the cable modem up, we'll just dump that buffer. So that's the sleep mode. You'll also see on this slide the buffers for the different profiles. And I'll get into that a little bit more in one of the next slides. On the right-hand side of the slide, you see something that looks like a duty cycle. We really are basically turning the modem on and off with a duty cycle. And it could be like 20 milliseconds on and 180 milliseconds off. So it's like sitting in a big lecture hall at college where every time there's a new slide, you wake up, you look at the slide, and you go back to sleep. Next slide comes up, you wake up, and you go back to sleep. So we pull all this together and we take a look at what the downstream block diagram looks like. We get this. We have packets coming through a forwarding engine. They go down into the cross engine where we apply the DOCSIS rate shaping. There's a DLS buffer that holds onto packets. Each packet gets tagged with a profile that it belongs to. These go into profile buffers. From there, the PHY layer is able to take bytes out of these profile buffers and map them into FEC code words. And that's where we have the code word builder. This code word builder, when it maps bytes from a profile A or profile B or something, it creates a tag and attaches it to that next code word pointer we talked about earlier. So that code word pointer contains two things. It contains a profile ID and a pointer to where the code word is. It then slams that into the OFDM structure on the right. Up above we have our control plane, which comes down and we end up having the message channel that drives into the PLC. The message channel contains those boot messages. And then the energy management channel sends energy management messages down to the cable modem to turn on and off. We also have a timestamp that's mixed in there as well. The upstream is equally fascinating. So you'll remember in the upstream, we actually don't have a lot of bandwidth on the plant right now. We've got 5 to 42 megahertz. It's working great, but we do have an ability to expand that bandwidth. But even within that 5 to 42, DOCSIS 3.1 will give you a good bang for the buck. In blue here, we see the current carriers that you might have with a 3.0 modem. SC stands for single carrier. So we've got, in this example, 4 carriers that are turning on or off. We can integrate DOCSIS 3.1 OFDM-A on top of the single carrier QAM from 3.0 in both frequency and time. So what do I mean by that? Well, we could create an OFDM channel that all the way from 5 megahertz to 42 megahertz and use the spectrum, let's say in this example, below 20 megahertz and stuff that's above, let's say, 38 or 40 megahertz. So it can frequency share. It can use the frequencies that 3.0 is not using. In addition to that, when 3.0 upstreams are not transmitting, we can expand the OFDM channel in there to fill the gaps. Now, there is a little bit of guard time and frequency that is needed as we surround it. There's about a 1 megahertz lost for guard time that we have to observe. But fundamentally, we can fill in the spaces. That means that if you have a lot of 3.0 and not much 3.1, you have a small amount of space for 3.1. If you have a lot of 3.1 and not much 3.0, you have a large amount of space for 3.1. but we can completely use up the spectrum. That is an efficient system, and that is one of the most powerful features of 3.1, is that it can coexist and use common spectrum with 3.0 in the upstream. Another interesting feature that I'll just briefly mention with DOCSIS 3.1 is that we have a timing protocol built into 3.1, where we can end up supporting 1588 timing coming out of a cable modem to support timing services. That brings me to my last slide. I just want to touch on some of the highlights here. We talked about a little bit about registration and operation. A lot of the 3.1 concepts are really just 3.0 concepts modified for OFDM and OFDMA. So you'll see a high level of operational familiarity. We're still using bonding. In 3.0, we bonded across QAM channels. In 3.1, you can bond between OFDM channels and QAM channels. There's a new version of QoS, which we call a hierarchical QoS, which allows you to describe what you want to have happen across service flows. And then there's some active queue management, which actually prevents things like buffer bloat, which is a buildup of packets and buffers, so we can get better performance with TCP. With that, I'd like to pass the baton over to George Salinger, who is the Vice President of the Access Network Architecture team at Comcast. Take it away, George.
Thanks so much, John, and good morning, everybody. I'm going to talk a little bit about migration and how potentially how MSOs may migrate from one version of DOCSIS to another. And this is no different than what we have done in the past. Perhaps there are some differences here in that, you know, DOCSIS 3.1 will implement OFDM and OFDMA and the upstream, and so there are some intricacies of how would we do that. But what I will cover is a bit of an example. It does not mean that anybody has to do exactly what I've outlined here. These are just examples of how things may evolve. And starting with today, as I show in the slide that you hopefully are seeing, most of us have lots of DOCSIS 2.0 devices, many DOCSIS 3.0 devices. On the CPE side, perhaps a few 1.0 devices still in the network, and on the head-end side, we probably all have either 5 to 42 or 5 to 65 megahertz upstream capacity. Many of us have deployed DOCSIS 3.0 CMTSs with downstream channel bonding and have legacy out-of-band to worry about. Soon we will, before DOCSIS 3.1 becomes available, we will be deploying more DOCSIS 3.0 devices. Almost all of us are deploying exclusively 3.0 devices, and perhaps removing DOCSIS 1.0, 1.1 devices from the network. On the head-end side, we're all either in the process or considering to deploy CCAP devices with more downstream capacity, deploying perhaps upstream channel bonding, and in some cases, depending on the number of upstream channels, deploying SCDMA. As we foresee what will happen in the network, we think that in general there'll be a CPE, DOCSIS 3.1 CPE, that will appear first in the market, and so we'll probably deploy this DOCSIS 3.1 CPE, but still using the 3.0 equipment in the head end. And so by then we'll have many DOCSIS 3.0 CPE devices and begin deploying DOCSIS 3.1 devices, but operating them in 3.0 mode. This is what the blue represents. You'll start seeing red representing DOCSIS 3.1 operation in the network. So, having DOCSIS 3.0 devices in the field, beginning to deploy DOCSIS 3.1 CPE, but continuing to use it in DOCSIS 3.0 mode. Eventually, 3.0 head-end equipment will become available, and when that is the case, then we'll start deploying that equipment and deploying it perhaps in a gradual manner, and beginning to operate DOCSIS 3.1 CPE devices in DOCSIS 3.1 mode. In other words, making some portion of the spectrum available perhaps in the downstream first, with DOCSIS 3.1 OFDM downstream capacity, and begin leveraging that capacity on the CPE that supports it. For those devices, for those 3.1 devices that are deployed, for which we may start deploying or start enabling DOCSIS 3.1 OFDM capacity, we could bond the the downstream, the DOCSIS 3.0 downstreams with DOCSIS 3.1 downstreams. And so, for example, we might have 16 or 24 DOCSIS 3.0 downstreams, and, for example, 24 megahertz of DOCSIS 3.1 capacity, OFDM capacity. We could bond that, all that capacity together, and so DOCSIS 3.0 devices will not see the 3.1 OFDM blocks, but the 3.1 devices will. Then eventually we might start deploying the upstream when the upstream line cards become available. We might begin deploying DOCSIS 3.1 upstream capacity and begin using that additional capacity for the modems that support it. A couple of things that are interesting about the upstream. While the upstream line cards may become available after the downstream line cards, it is not necessarily the case that one needs to deploy downstream capacity in order to use the upstream DOCSIS 3.1 capacity. For example, an operator may decide to not deploy additional downstream capacity, 3.0 or 3.1, but begin deploying DOCSIS 3.1 upstream capacity when the line cards become available, and use it simultaneously, in the same portion of the spectrum, in the 5 to 42 or 5 to 65 portion of the spectrum, until additional capacity becomes available. DOCSIS 3.1 provides this ability to time division multiplex DOCSIS 3.1 upstream bursts with DOCSIS 3.0 upstream bursts, and so it's possible to begin using the upstream capacity even before the downstream capacity becomes available. So the stage in which, or the order in which, the downstream and upstream may be deployed may vary from one operator to the other. In general, I think most of us will begin deploying downstream DOCSIS 3.1 capacity when it becomes available, because it is much more, it uses much more efficiently a spectrum at about 50% gain in capacity for the same amount of spectrum, for the case in which we can use most of the modems at 4K QAM. In the case where, in the case where not sufficient SNR is available for running modems at 4K QAM, then these modems will run at a lower modulation profile through the availability of a feature called multiple modulation profiles, like John explained before. So it stands to reason that if additional capacity is deployed and DOCSIS 3.1 CPE and head-end equipment is available, that one would prefer to use the OFDM higher modulation order option, because it uses spectrum more efficiently. But in the upstream, we may start using it even on the current spectrum because of the time division muxing functionality. Eventually, different MSOs may choose to deploy additional capacity in either the downstream or the upstream. For example, expanding the downstream to 1.2 gigahertz or expanding the upstream to 85 megahertz or more, and therefore have additional capacity to support DOCSIS 3.1 devices. In the next few slides, I'll quickly go through them. I depict the same migration strategy, but now showing a spectrum view of things. So it's a different view of the same thing. In this slide, I show what we would have today. For example, 8 downstream DOCSIS 3.0 carriers, 3 upstreams, or any number between 1 and 3, as an example of upstream DOCSIS 3.0 carriers, and the presence of legacy out-of-band for those of us that do have it. Then eventually, as we deploy more DOCSIS 3.0 equipment and we need additional capacity, we would have more downstream carriers and perhaps even more upstream carriers, as is depicted in the picture that is shown now. In the next picture, I show DOCSIS 3.1 devices to begin their deployment. And as it can be seen from this slide, there is no OFDM or OFDMA deployed. The DOCSIS 3.1 devices are operating in DOCSIS 3.0 mode, so it provides a means for cap and grow, capping the deployment of 3.0 devices or prior generation devices and begin to deploying new generation devices. In this slide, I show how DOCSIS 3.1 CCAP devices become available either in the downstream or in the upstream or both, and how the spectrum could be utilized to support DOCSIS 3.1 devices. In the case of the downstream, the spectrum is not shared, so the spectrum that is assigned to DOCSIS 3.1 would be used for OFDM, and so the 3.0 modems and prior generation modems would not see that capacity, but the DOCSIS 3.1 modems would see that capacity and would be able to bond it with all of the existing capacity for DOCSIS 3.0. In the case of the upstream, both 3.0 and 3.1 devices would be able to use the entire available spectrum through this TDM feature of DOCSIS 3.1. Then eventually additional spectrum could become available or could be made available, and when that is the case, for example, in the upstream, we could expand the upstream capacity to 85 megahertz. DOCSIS 3.0 devices, or at least 3.0 devices that were built to support 5 to 42 megahertz, would only see that part of the spectrum because of the way the diplex filter is built. But DOCSIS 3.1 devices that would be built to support 85 megahertz and above would see that additional portion of the spectrum and therefore would have additional capacity. And the same thing in the downstream. If we expanded the downstream capacity to 1.2 gigahertz, as is currently required in the spec, then DOCSIS 3.1 devices would benefit from that portion of the spectrum or that additional capacity. Eventually, we could expand the capacity. DOCSIS 3.1 contemplates the support for additional capacity in the downstream up to 1.7 gigahertz. And when and if that capacity becomes necessary and available, then we could use that capacity as well. So with that, I'll pass it back to Mike Roebuck. Thanks so much for everybody, and my email address is in the slide if you have any questions or comments.
Thanks, George. I think you did that without taking a breath the whole way through. So we're probably going to go over our time limit here. We were slated for an hour. We've got so many questions that I think we're probably going to go over just a little bit, maybe 10 minutes. So hang on. We'll try and get your questions answered. We're going to start at the very bottom of the question queue. And how do you compare DOCSIS 3.1 and EPOC in terms of availability and functionality? So I think for this question, why don't we start off with Jeff, then we'll go to John, and then we'll circle over to you, George. So question number 10.
All right. Thanks, Mike. So how do 3.1 and EPOC compare? So at the physical layer, it's a possibility that EPOC may decide to use the DOCSIS 3.1 PHY. So at that level, there'll obviously be a great deal of commonality. Up at the MAC layer, it's pretty much significantly different because EPOC is going to be implementing the equivalent of the MPCP EPON protocol over a coax, and DOCSIS 3.1 is going to be implementing a completely different MAC. But in terms of the functionality, there should be a great deal of similarity in terms of the amount of spectrum that both can use.
So the comment I would add on, first of all, what is EPOC? EPOC is a technology we developed in the IEEE, which allows you to run down a fiber run with EPON or Ethernet, actually EPON, and then at the end of that fiber run, convert to coax. So it's an EPON over coax technology. As Jeff mentioned, EPOC and DOCSIS 3.1 are going to use the same PHY. So their fundamental ability to get capacity out of the coax link is the same. I think there's two differentiating features. One is right now DOCSIS is essentially located in the hub and not out in the plant, which is where EPOC is. So that's one difference. We are doing some work on DOCSIS with remote PHY and other technologies to push the PHY out into the plant so that we can have equivalent connectivity as EPOC. So connectivity and productization is one aspect of it. I think the other differentiation, though, is 3.1 allows spectrum sharing with 3.0. We physically can have the same spectrum support single carrier QAM or OFDM in the upstream. In the downstream, we bond between legacy QAMs and OFDM, whereas EPOC really requires its own spectrum. So if you have 8 or 24 channels in your downstream dedicated to 3.0, and you want to add OFDM on top of that, you could add 24 megahertz of OFDM and use all the old spectrum and the new spectrum for your 3.1 modem. Whereas EPOC would only be able to operate within that new spectrum. Thank you.
And this is George. I would just add to what John and Jeff said that EPOC does give us one additional option, one additional tool in our toolbox for deploying high-speed data services or commercial services, And there's one additional difference or feature of Epoch that may be beneficial, and that is the implementation of a TDD mode, time division duplexing mode, where we could conceivably use a spectrum, for example, a spectrum above 1.2 gigahertz for upstream and downstream, whereas in the other approaches where they're all FDD, the FDD mode, we'd have to dedicate some part of the upstream and some part of the downstream for the purpose of Epoch. So another tool and a mode of operation that we didn't have before. Back to you, Mike.
Okay, thanks, George. All right, moving on to question 19. We'll direct this at you, and then we'll circle over to Jeff after you answer. DOCSIS 3.1 upstream is OFDM. Is this suitable for RFOG types of systems, and how would this work?
It is definitely suitable for RFOG systems. I think the main challenge will be from the expansion of the bandwidth as opposed to being an OFDM. In the current DOCSIS, we have multiple transmitters with multiple channels, and the same thing can happen with an OFDM signal where different subcarriers are being shared by different users. But now that the bandwidth is going to be much larger than the bandwidth of DOCSIS 3.0 systems, the likelihood of simultaneous transmissions will be higher, a little higher than the DOCSIS 3.0 system, which results in more opportunities for the optical beat interference events. But there are solutions for this particular problem, so I don't see any issues with RFOG being operating with DOCSIS 3.1 systems.
Okay, Jeff, anything to add on that one?
No, I think he nailed it.
Okay, all right, we'll keep moving then. All right, moving over to 20, which came during Jeff's presentation, and John also wanted to speak to this one as well. How can we efficiently operate DOCSIS 2.0, 3.0, and 3.1 devices on the same network? And before you start, Jeff, if you guys maybe could be thinking about certain questions that I haven't assigned, if there's something you want me to ask, just let me know and we'll circle back to those. But back to question 20 and Jeff and then John.
Well, we've been delivering different technologies for years over the coaxial plant. I mean, today we have FSK, BPSK, all sorts of telemetry, DOCSIS 1.0, 2.0, 3.0. We actually have OFDM for those of us that have deployed circuit switch telephony. So I don't see this being any different than what we've done previously. The difference here is that you've got a single edge device that has to manage the scheduling of this. And the folks that are developing those edge devices, the CMTS vendors, have quite a few years of experience doing this. So I don't really see there being any issue.
I think one of the things that works well in our favor is all those new 3.1 modems that are going to be coming out actually have 3.0 modems inside of them as well. So when you deploy your modems, it can come up in 3.0 mode and work on a 3.0 plant. If there's a 3.1 plant, it could do all 3.1, but the most likely mode is a hybrid mode where it's running packets over both a 3.1 PHY and a 3.0 PHY. And in the DOCSIS spec, we manage that by bonding in the downstream across the 3.0 and 3.1 PHYs. And in the upstream, we keep the 3.1 PHY, but we allow it to fill in the gaps in both time and frequency. So we have a full backwards compatibility story.
Okay, thanks, John. So we have a couple of questions here in regards to deployment schedules, product availability. Why don't we just run through the panel real quick? We'll start off with you, IHAM, and then we'll go over to John as far as the product side of DOCSIS 3.1, and then finish up with Jeff and George as far as cable operator deployment plans, schedules, that type of thing.
I think that DOCSIS 3.1 devices will start to appear soon now that the DOCSIS 3.1 spec got issued. I think that the CPEs will start to appear as soon as early maybe as next year, and then the following year we'll see some CMTS products, probably mostly in the downstream first, and then the upstream, as George mentioned in his migration slides.
John, anything to add from the Cisco point of view there?
Yeah, I'm going to go a little bit more conservative. I think we're going to see stuff in the lab next year, but I think we have a lot of work ahead of us to get everything up and running. I'm going to really say that DOCSIS 3.1 is a 2015 to 2016 time frame from a field perspective.
Okay, cable operator perspective, Jeff, why don't you start?
Yeah, I think I'm even going to be a little bit more conservative than John. I think that we're going to get some of the equipment next year as new silicon comes out. But as we've seen with each new release of DOCSIS, it can take a year or more in the lab doing integration testing, getting your tools to be able to monitor it, getting the technicians trained on how to configure the levels. There's a lot of activity going on for cable operators. We're deploying either now or shortly in the future. CCAP, we're working on the plant, we're splitting nodes, we're tweaking things, we're maybe even considering moving the split. To throw something else on top of that, it's going to take a little bit longer from our side than I think a lot of folks may be anticipating. So we just need to take that into account in our plans, all the other activities.
And this is George. I agree with Jeff. I think from an operational perspective, any deployment takes time. I think in general we're going to start seeing, I'm going to echo what most people said here, I think we're going to start seeing lab devices, CPE lab devices, and even head-end lab devices towards the end of 14, beginning of 15. I think we're going to, from what we've gathered, we're going to start seeing commercially ready for deployment devices in the middle of 15 or so. I think commercial deployments are going to start, towards the end of 15, and then by 16, I think they'll be pretty massive deployments. But it'll take time. It's not about, I think we said this time, it's not about replacing what we have. It's about adding capacity with the new devices. So as we need new devices, for in the future, in the 15, 16 time frame, we'll start buying 3.1 devices, and we'll start buying more and more as the price gap begins to shrink. There will be inevitably, a bigger price gap earlier than later, and as the gap becomes smaller and smaller, we'll be buying more and more devices until at one point we'll start buying exclusively 3.1 devices. Just the same thing that happened with 3.0. Then on the head-end side, I think the additional capacity, as we need additional capacity, we'll start buying head-end equipment that's capable of running DOCSIS 3.1, both in the downstream and the upstream. So it'll be a very gradual, I agree with Jeff, it'll be a very gradual thing. It'll take a long time to deploy.
Okay, thanks, George. All right, so we got a ton of questions here still, so we're going to try and keep knocking some of these out, and we'll just go to question 62. IHAM, what are the weaknesses of OFDM, for example, group phase delay, etc.?
Yeah, so OFDM has many strengths and maybe a few weaknesses. I guess sensitivity to phase noise is one of the weaknesses for OFDM. Also, it needs tight accuracy for frequency as opposed to maybe time for SCDMA. Also, some of the perceived weaknesses for OFDM is the peak to average power ratio being a little too high. Some simulations were done to compare an OFDM signal with multiple single carrier signals, and it turned out that the OFDM signal doesn't have a worse peak to average power ratio than 8 to 16 single carrier signals. So it may not be it won't be a drawback or a weakness for OFDM when it is employed with DOCSIS 3.1.
Okay, anybody else want to tackle that one, or is that covered? All right, well, I'm sorry, was there someone that wanted to speak?
No, I think AHAM covered it. Okay.
All right, so let's just go to George, question 46. What is the migration strategy? I think you might have answered this already. What is the migration strategy for moving the upstream split to 85 megahertz? How does the modem handle the different diplexer?
Yeah, yeah, I try to cover that a bit in my slides. I think initially, well, first of all, modems that are compliant with the DOCSIS 3.1 spec must support 85 and current splits, right? So a modem for use in in North American systems would have to support 42 and 85 megahertz with a switchable diplex, and modems for European systems have to support 65 and 117 megahertz. So the migration initially, the deployment initially would be for 42 megahertz or 65 megahertz, and then if and as the split is changed, these same modems will support, through the diplex filter, switchable diplex filter, will support the new part of the spectrum. Older modems would still exist and still be able to operate. They'll just operate in the lower part of the spectrum. They will not operate in the newer part of the spectrum. With respect to, I saw a question about out-of-band. The out-of-band, for those of us that use it, will need to move it. It's feasible to move it. Some set-top boxes will need new code. We are getting new code for them in order to move them. And so that is doable as well. You would have to move them out of the way, and that's the reason we picked, in general, 85 megahertz so that we can have the out-of-band operate above that part of the spectrum. So I think the upstream in general, to summarize, the upstream will start at the current spectrum that we use, and then if and as we need it, we will expand the upstream. We'll move the upstream to 85 or 117 or even 200 megahertz. Some people might move it to even that higher, and use it upon it becoming available.
Okay. All right. Thanks, George. So we are over our hour. So what we're going to do is we're going to get our final thoughts here from the panel, and we're going to start off with IHAM, and he's going to answer question 47. The comment that 3.1 can be deployed without plant changes does not ring true, as added U.S. spectrum requires, upstream spectrum, requires diplexer changes and active device changes for the head end, and the OSP, does it not? So IHAM, if you could answer that, and then give us your final thoughts, and then we'll go to John, and then we'll go to Jeff, and we'll finish this up with George.
Absolutely. Thanks. So basically, this is a good question, but I wanted to emphasize that enabling DOCSIS 3.1 does not need the outside plant changes, meaning that deploying DOCSIS 3.1 CPEs and operating the OFDM and obtaining the gain from the LTPC, this can all happen with the current spectrum, 5 to 42 or 5 to 65, along with the downstream spectrum. So you can get the benefit, the added throughput, the added capacity of DOCSIS, some of DOCSIS 3.1 features with the current spectrum, with the current plant and current spectrum as is. But the moment that you need to emphasize on the capacity growth enabled by DOCSIS 3.1, that definitely needs outside plant changes, and that can happen over time. It is important to know that enabling DOCSIS 3.1 over a few steps is key to get familiar with the technology, is to increase the number of CPE devices to a good amount of percentage, basically, to justify allocating new spectrum. And after that, you can grow in terms of spectrum. Some final thoughts about DOCSIS 3.1. It is a really new and cool spec that's using cutting-edge technologies like OFDM and LTPC. It gives us a lot of increased capacity compared to DOCSIS 3.0 systems. It promises a lot of cost drop potential, and also a differentiating feature for DOCSIS 3.1 is backward compatibility when it is compared to other technologies like EPOC. So it can accommodate legacy equipment and capitalize on the head-end equipment that's already in the field. And with that, I would turn the mic to John.
Hi, Mike. Thanks, IAM. A couple of thoughts. One, on the 85 megahertz. You don't have to upgrade the plant for DOCSIS 3.1, but at some point in time, you're going to want to, if you want additional bandwidth in the upstream and the downstream. And there's no really way around it. It's one node at a time. I mean, you got to go out and start over time upgrading nodes, and that doesn't happen quickly. Our recommendation would be to start that tomorrow. Just every single node split going forward, put in 85 megahertz. Or 200 megahertz if you feel you could be aggressive with the bandwidth earlier in your deployment. clear out the bandwidth, below, stop using frequencies below, let's say, 110 megahertz, whatever cutoff you choose, and just start rolling over nodes one at a time. 3.0 can use that bandwidth, and when 3.1 comes out, it can use that bandwidth as well. It's just one of those things that you start doing now, and by the time 3.1 comes out, maybe 10% of your plant's ready for it at a higher frequency. That's huge. The second thing I'd add is 3.1 it's the right long-term roadmap for us to head in. But it's going to be 3 or 4 years before it hits the market in stride. We have a lot of room left on 3.0. We still have the whole 24-channel downstream and 32-channel downstream cable modems and gateways coming out. So there's a lot of life left in 3.0, which means there's a lot of bandwidth that the operators can deploy this year and next year that makes DOCSIS probably the most competitive technology in the marketplace. So don't hold back on 3.0 waiting for 3.1. Go full bore with 3.0, and when 3.1 comes along, jump on that, and it integrates in really well with anything you've deployed. Thanks. Thanks a lot for everybody, by the way, for attending today.
So I'll glom on to what John was talking about and take one point and say that not only does DOCSIS 3.0 have a long life, it has a long useful life, as does the HFC plant itself. That with 24 by 8s and 32 by 8s for DOCSIS 3.0, and then the newer devices that have the ability to run in 3.0 mode and can move over to 3.1, that gives us a very, very good lifespan, a very long useful lifespan of DOCSIS 3.0. Upstream is a different challenge, and that's something we all have to keep our eyes on, and we can deal with a lot of that through our business as usual node splits, reduction in cascades, et cetera, et cetera. Now, by planning this out and looking at it, there's a lot of things that have to happen, whether it's an analog reclamation, getting rid of SDs and only having HDs, getting rid of MPEG-2, moving it to MPEG-4 to create this space in which we can put 3.1. That is something that we have to plan out. And as we look at our planned speed increases and even projecting that line out a little bit longer, as I sort of covered in my slides, we can look a little bit forward and try to reach that point in whatever percentage of our demographics require that additional capacity. So the advice that I would leave you with is do some forward planning, reclaim as much spectrum as we can at the low end, as John suggested. When the devices are ready, start seeding those devices. But 3.0 has a long useful life left to it. So plan this out carefully and take every little opportunity we get to plan that out so that when the time comes that we do need it, we're ready for it. So George?
Thanks, Jeff. And I would just add to what Jeff just said, that in DOCSIS 3.0 we do also include support for 85 megahertz and 1 gigahertz in the downstream. This has been in the DOCSIS 3.0 spec forever, since it was first created. But MSOs have not needed that additional capacity. It is not easy. Like Jeff said, it's not easy to enable that capacity. It costs money, and it's a big operational change, such as, for example, going to all digital. It's a very complex thing to get done. Some operators have been able to do it quicker than others. Some operators have gone to switch digital video, making all the capacity available, and therefore not needed to make this change. As capacity growth continues, we will probably all need to expand the capacity that we provide, and at that point it will become necessary, and so we'll find a way to do it, and operationalize it. But with respect to DOCSIS 3.1, it's one thing to highlight. There's a lot of questions about when will it be available. We hear about anything like DOCSIS 3.1 or any development like this, and we want to know when it's available, and we sort of lose perspective on how fast or how slow things are evolving. And in the case of DOCSIS 3.1, I wanted to point out it's the fastest idea to product the version of DOCSIS ever, and the reason for that is because we need it so badly. We're all growing the amount of capacity that we're using to provide DOCSIS-based services, and more efficiency in the way to do that would be much better, and the sooner we can deploy it, the better. And so by way of comparison, DOCSIS 3.0, from the time we started with the idea until the time we started deploying, a period of about 6 years went by. In the case of DOCSIS 3.1, it'll be at the most 4 years. So it'll be probably less than 4 years. So it's considerably faster than any version of the spec that we've had so far. I've actually never been in a development of a DOCSIS spec, and I think I participated in all of them, in which during the development of the specification we can see products being developed. I've never seen that before, and I see that very clearly at DOCSIS 3.1. So with that, back to you, Mike. I think this is good. Thanks everybody for attending. I've never seen so many people attending a webinar like this one. It was over 600, almost 700 at one point.
Okay, great. Well, first off, I want to thank our panelists. I want to thank Jeff and George and Iham and John. And we want to thank all of you that took time out of your busy day to join us. Just a reminder that this will be available in on-demand mode on CED's website, cedmagazine.com, starting tomorrow. So that's going to wrap it up. Thanks again.